In this video, we discuss theorem 5.5 and 5.6 together. In order to prove 5.5, we will prove theorem 5.6 in 9 consecutive ways. So far, we have proved the family of fractional ideals form a semi-group, commutative semi-group with identity element as O. Now we prove every non-zero ideal of O can be written as a product of prime ideals uniquely up to the order of the factors. We prove this theorem in 9 consecutive results. The first result we will prove for any non-zero ideal A of O, there exist prime ideals P1, P2, etc. PR such that P1, P2, etc. P1 into P2 into etc. PR is contained in A. For a contradiction, suppose that it is not true. That means there exists a non-zero ideal A for which we cannot find this P1, P2, etc. PR such that P1 into P2 into etc. PR is contained in A. Now we can define a collection of ideals of this property. That means let S be the set of all ideals which does not possess this P1, P2, etc. PR with this property. So we can get a non-zero non-empty collection of ideals. That is, if we write S equal to set of all ideals, non-zero ideals, A of O with this property. Okay, A does not A is an ideal, obviously. A is an ideal of O which is non-zero, and A does not doesn't satisfy property 1. Okay, if we assume this set contains at least one element, we can say that this has a maximal element because O is a Noetherian ring. So if we choose A be the maximal element of S. So we can say that for A we cannot find P1, P2, etc. PR. In that case, A itself is not a prime ideal. If A is a prime ideal, then this A can be written as P1. Then this P1 is contained in A. Then that result 1 would be true. So we can assume if A is an element of this S, then A is not a prime ideal. If A is not a prime ideal means you can find B and C such that BC is contained in A with this property. B is not a subset of A and C is not a subset of A. Okay, the definition of a prime ideal is B, C contained in A implies one of them is contained in A. Okay, B is contained in A or C is contained in A. The ideal C is contained in A. So A is not prime means you can find B and C such that BC is contained in A, but this does not hold. That means BC is contained in A, B is not a subset of A, and C is not a subset of A. Now you define A1 and A2 in this manner. A1 is equal to A plus B, sum of two ideals. A2 is equal to A plus C. Now if you collect the product A1, A2, this A1, A2 is ideal A1, A2 is A plus B into A plus C. Then by taking product you can get AA plus AC plus BA plus BC. Our assumption is BC is contained in A. So this part is contained in A, and BA, since A is an ideal, this BA is contained in A itself. If you multiply elements of A with any element of O, we can get that is again an element of A. This is the definition of an ideal. So this is also a subset of A, and this is also a subset of A. So all these four terms are subset of A. Then Consequently, this A1, A2, ideal product of A1, A2 is contained in A itself. Okay, that is what you have written here. A1, A2 is contained in A. But we know that this A1 contains A because this B contains 0. We can get every element of A is an element of A1. Okay, and every element of B1 is also an element of A1. Therefore, A1 properly contains this A. A1 contains at least one element which is not in A. So this A1 properly contains A, A2 properly contains A. So we can say that these A1 and A2 are ideals. The property that A1 is A1 properly contains A. That means A1 is a larger ideal of A. Okay, so we can say that this A1 does not belong to this one. Okay, A1 is not a member of. A1 is not an element of S. Similarly, A2 is not an element of, because A is the maximal element of S. So any ideal larger than A would not be an element of this S. Okay, so we can say that these two ideals are not elements of this S. That means this we can find P1, P2, etc. Ps, a set of prime ideals which whose product is contained in A1, because A1 is not an element of S. Similarly, you can get another set of ideals and say PS1, PS2, etc. PR, which is contained in A2. But we know that this product P1, P2, etc. PS, PS1, PS2, etc. PS plus 1, PS plus 2, etc. PR is contained in A1, A2, which is contained in A. Okay, this is a contradiction because we can get ideals P1, P2, PR whose product is contained in A. So this is the contradiction for the choice of A as a maximal element of S. That means our assumption is wrong. So for every ideal A, you can find P1, P2, etc. PR such that whose product is contained in A. Of course, this P1, this product need not be unique. There can be another set of prime ideals whose product is contained in A itself. Okay, so we never prove the uniqueness of this inclusion. Now we can prove the second result. In the second result, we have uh, a definition first. Definition of A inverse. For any ideal A of O, we have A inverse. A inverse contains all the elements of K. This A is the this O is the ring of integers of K. Then we collect all the X from K such that XA is contained in O. Okay, this is the idea here. So this A inverse contains all the elements of uh, this A itself, right? Because if we multiply A, that is contained in A, that is always in O. So A inverse contains all the elements of A. That is trivial. And A inverse is a O submodule. By submodule we mean like subspace in a vector space. Okay, so we can easily prove that this A inverse is a O submodule. Like we how we prove this subspace. W is a subspace of V. If we choose alpha comma beta belongs to A inverse, and we need to prove that it is O submodule. Instead of F, we have this ring O. So if we choose C belongs to O, we need to prove that C alpha plus beta belongs to A inverse. Okay, so we can easily prove this. In order to prove this is an element of A inverse, we need to evaluate that C alpha plus beta times A. So C alpha plus beta times A is equal to C times alpha times A plus beta times A. But we know that alpha and beta are elements of A inverse, so this is contained in O and this is contained in O. Then it's sum which is contained in O itself. Therefore, we can say that this is an element of A inverse. Therefore, A inverse is a O submodule. If A is a non-zero ideal, then every element C belongs to A. We can get C A inverse is contained in O. Okay, because if we choose an element X from A inverse and C from A, we can say that XA is contained in O implies XC is an element of O. Okay, so this is what we have written here. For any C belongs to A, we can get C A inverse, that is C into any element of this A inverse. That product should be an element of O. So A inverse is a fractional ideal, because we can find a C such that C A inverse belongs to is contained in O. Then A inverse is a fractional ideal. This is the definition of fractional ideal. Clearly this O is contained in A inverse. Okay, if we choose any element of O, we can get this A is if we choose any element of O here, C belongs to O, then clearly X into this A, uh, C into A is always an element of O, or is contained in, this set is contained in O. Okay, this is the definition of the ideal A. Or these are the elements of this product are exactly the elements of O itself. Each element is an element of O. Therefore, we can get this is contained in O, and then for every element of O is contained in A inverse. So O is always contained in A inverse. That means A inverse, the inverse of an ideal defined here is a little bit large set than this ring of integers. So this expression would imply that by multiplying a with both sides, a is equal to AO. This, since a is an ideal, a is equal to AO, and AO is contained in A inverse, because O is contained in A inverse. So we can say that this A is always contained in A inverse. Okay, and A inverse is same as A inverse A, because we are considering only commutative rings. So this is A inverse equal to A inverse A, and that is always contained in O, because that is the definition of A inverse. If you choose any element of A inverse as X, then XA is always contained in O. So XA is contained in O for all X belongs to A inverse. This we can write it as A inverse A is contained in O. Okay, so we have this result: A inverse is equal to A inverse A, that is contained in O. Okay, that means A inverse A is an ideal, hence it is a fractional ideal. A inverse is also a fractional ideal. Then this product is a fractional ideal. A fractional ideal is contained in O if and only if this A inverse A is an ideal. Okay, so we can say that A inverse A is in fact an ideal of O. Another useful fact for the ideals P and A is that if A is contained in P implies this P inverse is contained in A inverse. Okay, that is very obvious. If we consider two ideals, A is contained in P, then once you consider an element X from A inverse, P inverse, then we can get XP is contained in O. X belongs to P inverse means XP is contained in O. This is the definition of P inverse. Since P contains this A, we can say that XA is contained in XP, which is contained in O. So we can get XA is always contained in O implies X is an element of A inverse as well. That means if whenever X belongs to P inverse, then X belongs to A inverse. So this A subset of P implies the inverses of these two ideals follows the reverse inclusion. Okay? Obviously, this O is contained in every inverse of every ideal. So O is contained in P inverse, that we have proved here itself. O is contained in A inverse for any non-zero ideals. So this O is contained in P inverse, that is contained in A inverse. This is an interesting fact that we have to use in the next result.